Let's continue our discussion with heat transfer by now talking about the mechanisms of heat transfer. Now, these are three different mechanisms: conduction, radiation, and convection. Conduction is the heat transfer through stationary matter by physical contact. So that is what we were talking about in the very beginning when we were talking about equilibrium. We were talking about two objects that were in thermal equilibrium. They were in contact with each other, not moving, and that was by conduction. Convection is the heat transfer by macroscopic movement of a fluid. So we'll talk about that in a minute, but basically, convection would be hot air rising and cold air sinking. Then we have radiation, which is heat transfer by electromagnetic radiation being emitted or absorbed. So this is an example of all three. We have conduction of the fire, the fire heating up the floor by conduction. Then we have the hot air rising through convection and cooler air that has cooled down in the higher point in the living room, the living room, and it's cooling, it's sinking, and so forth. So we get this convection happening. Then we have radiation, which is what we can kind of feel when we're close to the fire on our hands or maybe our feet. If it's a campfire, that would be by radiation. Okay, so let us talk about each of these individually. So, the rate of conductive heat transfer through a slab of material is P, that is the rate, is equal to dq dt, or equal to K times A times TH minus TC over D, where P is the power or rate of heat transfer in watts or kilocalories per second, A is the surface area, and D is the thickness of the material. TH is the temperature of the hot material minus the temperature of the cold material, TC, is the temperature difference across the slab of material. And K is the thermal conductivity of the material, and that is, again, listed in a table in the textbook, table 1.5. So we have two figures to look at here. So for conduction, we have a transfer of energy from hot to cold. So we have heat conduction. Heat goes from hot to cold, and we have the higher energy, let's see, the atom, we can call it, or molecule, that comes into contact with the other surface, which has a low energy, and it has a cold temperature. And so they come into contact, and this will have a lower temperature, and this has a high temperature. And so we have this heat transfer. So here is another way to look at it. So we have two slabs of material, hotter material, colder material, and heat going from hot to cold. The temperature is shown here as well. Hotter temperature, TH, is greater than TC. We have some distance between them. I'm sorry, the thickness. This is the thickness, not distance. D is the thickness, and the material has some conductivity K. So this is how you can calculate that rate of conductive heat transfer. Now, this can also equal negative Ka, or the thermal conductivity, times area, times dt dx. So dx being that thickness, dt being that change in temperature. Let's look at convection now. So convection is the thermal energy, where thermal energy is carried by the large scale flow of matter. So it's not just individual molecules, it is large scale flow of some sort of liquid or gases. So we have two different types of convection. We have forced convection, which is the flow that's driven by something like fans or pumps or something of the like. And then we also have free or natural convection, which is the flow that's driven by buoyant forces. So hot fluid rises and cold fluid sinks due to density decrease as temperature increase. So we have an example here, a boiling pot of water. So the colder water will sink to the bottom, and then the hot water will rise. And so this is what we see, and that's why we get like boiling water, or even in the winter, if you have a stove or a fire you can have going, it's usually hotter, maybe on the second floor, or if you're standing up, than being on the ground. Or in the summertime, you'll usually see, maybe you'll see dogs or something laying on the floor because that's where it's the coolest. And the last type is radiation, and the rate of heat transfer by radiation depends on the wavelength of electromagnetic radiation. So if we have a shorter wavelength or a higher frequency, this corresponds to a higher energy. So short wavelength, high energy. Okay, and we can also think of this in terms of colors as well. We have blue versus blue, oh sorry, that's just smaller, but blue versus the red hot up here. So the shorter wavelength, this is actually where it is the hottest, where a fire is the hottest, is at that point. And it's cooler as it goes up here. This more orangey color is going to be where it's cooler, the fire. All right, let's talk about radiation and emissivity. So the rate of heat transfer by radiation can also depend on an object's color. So black is the most effective and white is the least effective at heat transfer. So we can see, for example, these two sets of ice cubes, one on a lighter concrete, one on a very dark concrete or maybe an asphalt. So the lighter concrete is not taking in as much heat as the black asphalt, we can say. So there's not as much heat transfer here, so the ice doesn't melt as fast as the ice that is on the asphalt over here. So we represent this with an emissivity, and a black body radiator would have E is equal to 1, so that would be a perfect black body, versus a perfect reflector or transmitter would have E equals to 0. So let's look at this figure here. So we have a gray color or maybe even black with some sort of absorbed energy. So we're trying to absorb the energy here. So we get a lot of this incident energy, or this ray of light, coming in and staying in. It's being absorbed. Now when we're trying to radiate some of this, we can radiate a lot of it or emit a lot of it and retain just a little bit. So this is for a black body. Now over here, on the other hand, we have a silver-coated, or that would be more of the reflector. So In this case, we have a lighter color, and we're going to reflect a lot of that energy and only absorb a little bit. Versus radiating, we don't radiate a lot, but we emit just a little bit. So we retain most of that energy throughout this this object, whatever it may be. So I know that was just kind of a lot of mumbo jumbo with that, but why is this important? Think about when you are out on a summer day and you're wearing a black shirt. Okay, that black shirt is going to be absorbing all of that heat from the great sun. So the sun is giving us all of its rays in the summer, and it's so lovely until you're wearing a black shirt and it is really, really hot. Versus wearing a white shirt. White shirt will probably keep you cooler, a lot cooler than wearing a black shirt. So you'll notice that difference, and this is definitely something that we can see in day-to-day life. All right, so to calculate the rate of heat transfer that's emitted by radiation is described by the Stefan Boltzmann law of radiation. So P is equal to sigma A E T to the fourth. So what is sigma? Sigma is the Stefan Boltzmann constant, and it's given here. It does not change. This is a constant. So it's 5.67 times 10 to the negative 8th joules per meter, seconds meter squared, Kelvin to the fourth. A is the surface area, E is the emissivity of the object, and T is the temperature in kelvins. And again, P is our heat transfer. Now, if we assume that an object with a temperature T1 is surrounded by an environment with uniform temperature T2, the net rate of heat transfer by radiation is equal to sigma times E times A, our area, times the difference between T2 to the fourth minus T1 to the fourth. So this is our net rate of heat transfer by radiation. And here is a quick overview of our problem-solving strategy for this heat transfer. So first step would be, like always, examine the situation and determine what type of heat transfer is involved. Then identify the types of heat transfer that are involved. Identify the unknowns, identify the knowns and what can be inferred, solve the appropriate equation for the unknown. So here is also a list. Conduction, we have our heat transfer. Convection, we have some different heat equations, and then convection. Oh wait, I labeled that twice. That last one should be radiation. Sorry, I will fix that. So this should be, we just cross that out now. This is radiation. We just looked at that. Okay, and then we substitute our knowns into the proper equations for a numerical answer with the proper units and check to see if the solution makes sense. Again, we always want to make sure our solution makes sense. All right, and again, we will look at some examples in person. All right, and that is all. If you have any questions, please feel free to ask. Thanks.